In this video, we're going to talk about the distance from a point to a line in either R2 or R3. There are two different formulas that we're going to prove in different videos. When we discuss the distance from a point to a line, we're referring to the perpendicular distance. So in other words, the distance d refers to the distance expressed in the first diagram, not any of the other diagrams. Notice that only in the first diagram is the line drawn from the lettered point to the line actually perpendicular to the line. And that's the distance that we're looking for. Intuitively, most people understand that right away. Well, there's a formula. The distance from a point, P naught x naught y naught, to the line defined by the equation ax plus by plus c equals 0 in 2 dimensions is given by the absolute value of ax naught plus by naught plus c all over the square root of a squared plus b squared. Now note that we can't use that formula to determine the distance from a point to a line in R3 because there's no Cartesian equation of a line in R3. This formula only works for distance from a point to a line in R2. Now, what we see here is the proof of this formula, and it's developed if you're interested in a separate video. But let's just do a few pragmatic examples. Let's determine the distance from the point P, negative 6, 4, to the line with the equation 5x minus 3y plus 15 equals 0. Well, we're just going to use the formula. Now, a, in this case, a is equal to 5, and b is equal to negative 3, and c is equal to 15 from the equation of the line. And x naught is equal to negative 6, and y naught is equal to 4. And using all that information, we're going to plug it into this equation. Well, we see that inside the absolute value, we get negative 30 minus 12 plus 15, and then inside the square root, we get 25 plus 9. So we end up with the absolute value of negative 27 all over the square root of 34. Well, that's equal to 27 over root 34, and we can rationalize our denominator and call it 27 root 34 over 34. So the distance from the point to the line is 27 root 34 over 34 units. Well, suppose we wanted to determine the distance from the point 15, negative 9 to the line with vector equation shown. Well, we need to get that line in Cartesian equation form to use our formula. So we look at this and we say, well, we've got a direction vector of negative 4, 3. So that means the normal vector will be 3, 4. If you know the normal vector of a line in R2, then you know the Cartesian equation almost of that line. If the normal vector is 3, 4, then the Cartesian equation of the line is 3x plus 4y plus c equals 0. Now we take a point that's known to be on the line. Since negative 2, negative 1 is a position vector for the line, that means the point negative 2, negative 1 is a point on the line. We sub that in, an x value of negative 2 and a y value of negative 1, and we get a c value of 10. What that means is that the equation of the line is 3x plus 4y plus 10 equals 0. Okay? So now, since we have that equation, 3x plus 4y plus 10 equals 0, we know that a is 3, and b is 4, and c is 10, and x naught is 15, and y naught is negative 9. And using all that information, we just plug those values into this formula. Now, what we end up with is inside the absolute value portion is 45 minus 36 plus 10, and inside the square root is 9 plus 16. So we get the absolute value of 19 over the square root of 25, which equals 19 over 5. So the distance from the point to the line is 19 over 5 units. And now we get this interesting question here. What we have are two parallel lines. We know they're parallel because the normal of the first line is 5, negative 12, and the normal of the second line is also 5, negative 12. So those are scalar multiples of each other. They're actually identical. So the lines themselves are parallel since the normals are parallel. So what we're going to do, we're going to imagine these parallel lines, and we're going to say, okay, all I need is a point on one of the lines. And then I'm going to determine the distance from that point to the other line. And then I'll know that since the distance is consistent, I will have found the distance between those two parallel lines. So, written out here, the distance between two parallel lines is equal to the distance between one of the lines and any point on the other line. We'll determine a point on line 1. So what we're going to do is we're going to let x or y have any value we wish. I'll let x equal 0. Letting x equal 0 and summing it into this equation right here, we get 5 times 0 minus 12y plus 60 equals 0. Ultimately, y equals 5. So we can figure out that the point 0, 5 is on line 1. So really all we need to do is find the distance between 0, 5 and the second line, which is the line 5x minus 12y minus 60 equals 0. So a is 5 and b is negative 12 and c is negative 60 and x naught is 0 and y naught is 5. And we plug those values into the formula shown right there. And when we do that, we get ultimately the absolute value of negative 120 over the square root of 169, which is equal to 120 over 13. And that's the distance between those parallel lines. Now, we also have a formula for the distance from a point to a line in R3. The distance from a point P to the line R equals R naught plus SM in R3 is given by the formula D equals the magnitude of the vector m cross qp divided by the magnitude of the vector m, where q is any point on the line, and m is the direction vector of the line, and p is the point that we're trying to find the distance of it to the line. That's the actual point given in the question. Now, notice you can't use that formula to determine the distance from a point to a line in R2, because in R2 there's no cross product. So we spend a few slides justifying this formula, and then we get into a practical example. We're going to determine the distance from the point shown to the line with that equation. Well, before we get too deep into this, we can say right away that the point P is the point negative 1, 1, 6. The point Q is the point 1, 2, negative 1. So we're going to be able to figure out the vector we need. And we know that the direction vector of the line in question will be 0, 1, 1. We're going to be able to use our formula pretty easily. So a point on the line is q, 1, 2, negative 1. The direction vector is 0, 1, 1. QP is the vector from the point Q to the point P, which is negative 2, negative 1, 7. The direction vector, as stated, is 0, 1, 1. We're just going to determine what is the vector QP crossed with M. To do that, we get negative 1 minus 7, which is negative 8. 0 plus 2 is 2. And negative 2 minus 0 will be negative 2. And so QP crossed with M will be the vector negative 8, 2, negative 2. Sometimes we talk about reducing normal vectors, but or direction vectors. We don't want to do that here because we're specifically using this vector that we're obtaining right here. What we really want it for is its magnitude. So don't go reducing the components there. So the distance from the point to the line will be the magnitude of m cross qp over the magnitude of m. In other words, the magnitude of the vector negative 8, 2, negative 2 divided by the magnitude of the vector 0, 1, 1. So we end up ultimately with the with root 72 over 2, which is equal to root 36, which is equal to 6. So the distance from that point to that line is 6 units.